Hi everyone. In this video we are talking about section 5.3 in your textbook, which is about the multiplication rule for probabilities for independent events. And we'll talk about what it means to be an independent pair of events versus a dependent set of events. Now, two events are independent of each other if they do not affect one another. And what I mean by that is the outcome or the success or the failure of one event does not have any bearing on the probability of success for the second event. And we say that two events are dependent if one of the events really does affect the probability of success for the other event. So maybe this is a little abstract, but we can give examples to really highlight what we're talking about. One example of an independent pair of events would be as if you called event 1 or E1, we're going to call that flipping a coin and getting heads, right? So heads on a coin would be a success for E1. And E2 is going to be rolling a die and getting a 3. And so you know that if you flip a coin and roll a die, the outcome on one of those is not going to affect the probability of the outcomes on the other. An example of a dependent pair of events would be if you had a bag of M&Ms of all different colors, and you reach into the bag, and we say E1 is that the first M&M you draw out of the bag and eat is a red M&M. And E2, that event will be that the second M&M you draw out and eat is red. But hopefully you can tell that E1 really does affect the probabilities of E2, right? Because if E1 is a success, you've removed one of the red M&Ms from the bag, and so your probability of E2 actually decreases if E1 is a success. So that's what makes those two events dependent. I have lots more examples though. So suppose you watch sports. E1 might be the event that the Texans win their next football game. And E2 may be the event that the Astros win their next baseball game. And of course, these are completely different sports. And so the success of one sports team does not affect the probability that the other is going to, win their game as well. So those would be independent events. And then on the dependent side, we can say E1 is that whenever we deal a card out of a standard set of playing cards with 52 cards, E1 would be the first card you deal as a diamond. And E2, the second card you deal is red. Well, if E1 is a success, then you've actually removed one of the red cards from the deck because diamonds are red cards. And so, of course, that's going to actually lower the probability of success for E2. So that's why those are dependent events. Again, it's just lots of examples, I guess, to drive this point home. If you were to randomly select an individual from the residents of the United States, and we say E1 is that the individual has a college degree, and E2 is the event that the individual ate chicken for lunch. Those would be independent because, whether or not you have a college degree probably doesn't affect very much the probability that you ate chicken for lunch. As an example of another dependent, suppose that you randomly select an individual. And so again, just like before, E1 is the event that the individual has a college degree. And now E2, we'll say, is the event that they have an annual salary larger than $50,000. But actually, in this case, whether or not you have a college degree as a resident of the United States really does affect the probability that your annual salary will be greater than $50,000, right? And so that's why these are dependent events. This is what we call the multiplication rule for independent events. So this only works for independent events, and this would fail if you had dependent events. So let me point that out here, is that this little rule, and take a moment to appreciate what it's saying, but this little rule does not work for dependent events. So I guess you have to be aware of whether or not one event is going to affect the probability of the other event. But what this is saying is the probability that you have success for both event number 1 and event number 2 is just equal to the probability of success for event number 1 times the probability of success for event number 2. So as an example, we'll work this out. If you roll a die and flip a coin, and we say E1 is heads on the coin, well, the probability of getting heads on a coin when you flip a coin toss, that's 1/2, right? 1 out of 2 possible outcomes. And then E2 is getting a 3 when you roll a die. Well, that probability is going to be 1 out of 6, because we're talking about 1 out of 6 possible outcomes. So these are both theoretical probabilities. Well, the probability of getting a success, both flipping heads on the coin and getting a 3 on the die, that's just going to be 1/2 times 1/6, according to my multiplication rule. So this is going to be 1 out of 12 as the fractional probability. New example. Again, suppose you watch sports, and let's say that the probability that the Texans win their next football game is 40%. And we'll say the probability that the Astros win their next baseball game is 60%. So if you want to know the probability that both of your Houston sports teams are successful here, we're just going to use that multiplication rule again. And again, we can use that multiplication rule specifically because we're talking about independent events, right? So this is going to be 0.4 times 0.6. Now 6 times 4 is going to be 24, so this is 0.24 for my probability that both teams will win. And finally, one more example. So suppose you randomly select an individual, and we say the probability that maybe this resident of the United States has a college degree is about 40%, and the probability that they ate chicken for lunch is about 20%. So then the probability of both of these being true, that you've randomly selected an individual that both has a college degree and ate chicken for lunch, that's going to be 0.08, using that, again, that multiplication rule for independent events. The last thing that we'll talk about before this video is over is the word at least. So make sure you are able to interpret mathematically whenever you see at least in a word problem. So this is my example. Let's compute the probability that at least one male out of 1,000, so you've got the sample size of 1,000. Compute the probability that at least one male out of 1,000 aged 24 years will die during the course of the year if the probability that any 24-year-old male survives the year is 99.86%. And that's really wordy, very verbose. So let me just point out a few things. If you were just looking at one 24-year-old male, the percentage chance that they're going to survive until this time next year is 99.86%. And what the question is asking is if you gathered together a group of 1,000 of these 24-year-old males, what's the probability that at least one of them is not going to survive the year, right? And so at least means greater than or equal to in math. And so we're talking about the probability that, the number of males that will die during the year is greater than or equal to 1. What's that probability? Well, the probability that any one of those is actually going to die. This is sort of one of those complement rule calculations. So for any one, the probability of death is going to be, let's see, 100% minus 99.86%. So this is just the complement rule. Because your two options here are you'll either survive until next year or you're going to die during the year, right? So this is a complement probability. And this 100% is just 1, and 99.86% is just 0.9986. And these types of easy subtraction problems are really tough for me, but that seems like it is about 0.0014 short of 1. So I think that's actually the probability of death for any one male. So that's not our solution yet. But our idea here is that if any one of these 1,000 dies, we're counting it as, the event has occurred right here. We're counting as a probability that it's greater than or equal to 1. And so what we're going to do is actually consider what's the probability that all of them survive. And maybe you don't see where I'm going with this immediately, but the probability that all of them survive means that every single one out of the 1,000 have to survive. And so this probability is going to be 0.9986 to the power 1,000. And the reason I say that is because for the first one to survive, it's a 0.9986 probability. And for every single one of these 1,000 males, their survival is independent of the other 999. And since they're independent, well, I can just multiply through those probabilities. And what does it look like when I multiply 0.9986 times 0.9986 1,000 times? Well, that's what we call 0.9986 to the power 1,000. Now, that's what exponents do, is repeated multiplication. So here I have my calculator, because I actually can't do this in my head. 0.9986 to the power 1,000. That probability is 0.246. And again, this is the probability that everyone will survive, right? And so what we actually want is the probability that at least one dies. And so you'll notice sort of the complement rule in action here, because when we perform this experiment, or we follow these 1,000 males, there's only two outcomes. The two possible outcomes that I'm thinking of for our experiment is going to be either all survive or at least one dies, right? And so these are complementary events. And so if I want the probability that at least one is dying, that's going to be 1 minus 0.246. And in other words, 1 minus that answer. So this is going to be 0.754. Or 75.4%. Okay. And this is our answer right here, in percent, as a probability. And this is maybe a little bit interesting as a question, a little bit morbid too, but you think the chance of any 24-year-old male surviving the year is pretty high, like 99.86%. That's actually a pretty good probability that someone like this is going to survive until next year. But whenever you get a really large sample size, right, you get a really large group of like 1,000 of them, it's a very high probability that at least one of them will die. So in large groups of people, this is the result you find. Okay, see you in the next video.